Tyrannosaurus, the tyrant lizard king, has been one of the most well-studied prehistoric organisms ever. It's only been known for a little over 100 years, but due to its characteristic value and badassery, it was an immediate star to the public and academics alike. Even though many other extinct organisms have been known for far longer than Tyrannosaurus, T-Rex has become the most well-studied extinct genus or species, with almost 20,000 citations in Google Scholar alone. New Tyrannosaurus remains are found every so often, but finding new ways to analyze old specimens is the way to go to find out all one can about this impressive beast. A brand new study lit up the three-dimensional networks of blood vessels that ate its way through the face of Sue the Tyrannosaurus and found some unnerving information about the animal's senses, facial coverings, and evolution. The specimen of Tyrannosaurus, known as Sue, or as its super special organizational nerd number FMNHPR2081, was found in the summer of 1990 by a group of workers from the Black Hills Institute in South Dakota. Sue is the most complete Tyrannosaurus skeleton ever found, but you'll get a different percentage value depending on where you look, ranging from 67 to 90% complete. Either way, Sue is only surpassed by the potential Tyrannosaurus from the dueling dinosaurs specimen, currently being worked on by the North Carolina Museum of Natural Sciences. The half-smooshed skull of Sue was sent through a CT scanner in 2000, CT scanners being rotating tubes that shoot X-rays in the hole. With Sue's skull, it was moved at increments of 2 millimeters, so the scanner got a bajillion slices through the fossil. Put together, that equals a 3D model that can also show you what's inside it. The evidence. The new study, published in January of 2022 on Paleontologica Electronica by Florian Boabdillah, Emily Lessner, and Julien Benoit, took to analyzing 3 nerves that make up the major trigeminal nerve of the skull. These canals were segmented and reconstructed digitally in 3D on the right, least crushed half of Sue's skull. Like most of Sue's skeleton, the bony canals of the snout's neurovascular system were extremely well preserved and in 3D. The trigeminal nerve is a nerve responsible for sensation in the face and motor functions, such as biting and chewing, present in most, if not all, tetrapods to greater or lesser extent. The nerve is divided in 3, the ophthalmic, maxillary, and mandibular nerves. The ophthalmic nerve tends to arc up over the eyebrow and across the forehead. The maxillary nerve lies through the maxillary bones, and the mandibular nerve runs down and along the dentary or lower jaw. Different groups of animals have slightly different arrangements depending on their facial structures. Mammals, for instance, have the most complex facial nerves as they have the most need for them. We're very smooshy-faced creatures. Reptiles, on the other hand, have simpler ones and more rigid facial soft tissues. Crocs use their nerves in the sensi pits on their skull for sensing vibrations in the water. The 3 main nerves of the trigeminal nerve were found intact in Sue's skull. Let's take a look at each one and their anatomy and see what the authors interpreted it to mean. The ophthalmic nerves in Sue are referred to as the nasal canals, as the ones which got sliced up via the CT scan are the ones found in the nasal bones. Sue's nasal canals have 3 major divisions. the frontal ramus, lacrimal crest, and nasal ramus. The nasal ramus is the bundle of nerves at the front of this whole complex mess. It runs parallel to the midline of the nasal bone before branching into two main bundles around the nostril opening, these being a short lateral bundle and a long medial bundle. The rest of the nerve goes back along the nasal bones and midline of the skull. This chunk of nerves is called the frontal ramus. The last bundle is the lacrimal canal, and it splits from the main bundle up onto the lacrimal bone where the lacrimal horns sprouted. These bundles may have been where the lateral and nasal arteries were stored when the animal was alive. I said before that this was the ophthalmic nerve, and that isn't entirely false, it's just a little complicated. It's the nasal canals, which would eventually connect to and become incorporated into the ophthalmic nerves, were the CT scan to continue beyond the snout. The next canal we are to be acquainted with is the maxillary canal. This bundle of nerves is organized very differently from the nasal canals. Since these nerves were helping to control stuff going on in the maxilla or upper jaw bones, they needed to be flat, super branched, and arranged in an array across the entirety of the maxillary bones, like you see here. As you can see, the maxillary canals run from the top of the bone all the way down to the tooth row. The main artery where the bundle begins originates below the eye socket before running towards the tip of the snout. Nearly a dozen smaller canals branch away from the main nerve towards the bottom of the maxilla from its origin to the end of the snout. Interestingly, they become more complicated and branched towards the tip of the snout. The authors suggest these canals supplied and innervated the skin that covered the maxilla through all of the holes that pockmarked the maxilla in regular rows. These holes are called foramina, and are also found, though far less organized, in crocodilians. Some of these smaller branches even dug their way into the tooth sockets as well as the areas of the maxilla where replacement tooth grew. The last bunch of nerves is that which ran along the lower jaw. These are the mandibular canals. It begins at the back here and runs along the bottom, branching upwards towards the foramina that pockmarked the jaw in organized rows, like the maxilla, as well as the teeth. What is really weird here is that the nerves at the top of the lower jaw run backwards along the edge before terminating in more holes. This matches pretty well the pattern observed in another Tyrannosaurus fossil, examined and CT scanned by Soichiro Kawabe and Soki Hatorai in late 2021. This one was based on a single well-preserved lower jaw bone, which was purchased for the Fukui Prefectural Museum, so doesn't provide as much information as what's been done here with Sue. But it's good to get overlapping confirmation across specimens of the same dinosaur genus. Besides this other rex bone, this arrangement of nerves in the lower jaw, where the nerves do a reverse Uno and climb backwards along the top and back of the lower jaw, has only been found before in an ichthyosaur. What does it mean? When it comes to understanding the soft tissues of animals like Tyrannosaurus, there isn't much to go on. There aren't any fossil mummies and barely anything in the way of skin impressions. Therefore, studying stuff like the trigeminal nerve is of extreme importance to our understanding of how to reconstruct these animals, as it lays some groundwork from which you can base stronger and stronger inferences. Now, we must take a truncated trip through the evolution of the trigeminal nerve in diapsids to understand where Tyrannosaurus fits into it. It's been hypothesized that the ancestral condition for the trigeminal nerve in diapsids was of a long tubular thing that ran parallel to the tooth row, with simple branches going off into the holes on the side of the lip of the jaws. This ancestral condition has survived in squamates, the lizards and snakes, and has been found in mosasaurs and ichthyosaurs. The ancestral condition for the nerve in the skull is similar to the nerve in the jaw, but it appears that the mandibular canal has remained much more conservative in how branchy it is throughout all lineages of diapsid reptiles, with only minor variations here and there. Fun fact, these nerve sets don't get all messed up in snakes and lizards that have venom glands taking up space in their face. The venom glands are attached to a whole different network of nerves, go figure. Of course, turtles lost all their teeth, and evolution totally messed with the bones of their skulls, but the nerves didn't change much. Now we come to an interesting feature observed in Sue's nerves. There's a highly concentrated bundle of nerves near the very front of the skull's snoot. The bones here are called the premaxillae. They form the tip of the snout and the front half of the nostril openings. You see, some animals have the nerves at this part of the skull connected to the ophthalmic nerve, while others have it connected to the maxillary nerve. So, what's going on with Sue? It's not completely clear, so two hypotheses have been created to explain it. In crocodiles, lizards, and snakes, the maxillary nerve is the biggest and digs its way into the premaxilla bones. In birds, it is the ophthalmic nerves that come down from the nasal bones and into the premaxilla bones. In most of our modern dinosaurs, this is because their maxilla bones are reduced and their premax bones make up more of the snout, so the maxillary branches of the nerves have also been reduced. The opposite is therefore true of crocs in lizards and snakes. This is moderately simplified, as there are some exceptions to this. The authors of the new study found that it is most likely that tyrannosaurs, like Sue here, had the avian dinosaur condition of the ophthalmic nerve coming down into the premax bones. As I stated before, the maxillary canals are relatively the same in most archosaurs and early diapsid reptiles. With Tyrannosaurus, the distance between the main canal of the maxillary canal and the lip of the maxillary bones is striking and sets Tyrannosaurus, as well as many other non-avian theropod dinosaurs, apart from other diapsid reptiles. The authors found that this was most likely due to the animal's deep tooth sockets. Tyrannosaurus were constantly growing new teeth behind the old teeth in a conveyor belt-like system that pushed old ones out. So they needed their nerves to contact the very deepest reaches of the tooth socket to provide both old and new teeth with nutrients. These facial nerve canals have been described and illustrated in a relatively small number of other dinosaurs. That's mostly due to lack of tech to do it and lack of good enough fossils that might preserve the canals. Among the Ornithischian dinosaurs, the canals are known for Psittacosaurus, Stegosaurus, Frutidens, and then there's the early sauropodomorph Plateosaurus. These dinosaurs had the more ancestral condition of the maxillary canal, seen in other archosaurs and diapsids. The primitive Ornithischian Lesothosaurus had a similar condition, but had way bigger holes in the jaw, which has been hypothesized to function to supply the cheek muscles. Ankylosaurs are different in having way bigger and more complicated maxillary canals, most likely to aid their super huge noses in warming air or sniffing out yummy bits. The mandibular canals have been figured for Fukuisaurus, Edmontosaurus, and Triceratops, and their simplicity suggests that their maxillary canals would also follow the ancestral condition of other dinosaurs, where the maxillary canals are known. Enough snout material is known for the sauropod Diplodocus, but there is no evidence of maxillary canals, which is weird since some maxillary canal info has been found in little baby titanosaur embryos from Argentina. Now we come to theropods. Spinosaurus, Neovenator, Halscaraptor, and Majungasaurus have been figured, and all of them depart from the ancestral maxillary canal condition, just like Sue does. All of them show a bunch of rows of holes along their snouts where the nerves connect to. Now, we need to figure out the possible uses for these canals and holes. Sensey snoots. Alright, so one major hypothesis for these holes and nerves is to sense the world. All crocodilians and some groups of birds have a ton of holes and a ton of nerves that branch into these holes. In crocodilians, these holes lead to what are called integumentary sensory organs. The big scaly beasts use these sensitive areas to sense minute changes in water pressure. Early crocodilians, phytosaurs, and rhysuchids didn't have the complex pattern of holes and nerves seen in modern crocs, so likely didn't have nearly as sensitive a snout as them. The birds that have these sensitive holes and nerves use them for tactile sensation, when they probe their beaks on and in the soil or water for food. That means that both closest living relatives to the non-avian dinosaurs have a similar sensitive nerve network that is seen in the non-avian theropod dinosaurs. A ton more research is needed on the specific adaptations and specializations needed for these sensitive organs, but the authors of the new paper think it is safe to say that the super-sensitive snout is a relatively modern, advanced feature that was absent in the ancestors of theropods and crocodilians, the Archosauriforms. The premaxillary nerve canals of Spinosaurus and Huscaraptor are particularly noteworthy among theropod dinosaurs as having the most branching pattern. This pattern is seen in crocodilians, Plesiosaurus, and Taniwasaurus. They are more branched and complex than what is seen in Tyrannosaurus. These are also semi-aquatic animals. It has been suggested by past researchers that the similarities between the super-branched nerves and holes of non-avian theropods and crocodilians supports a croc-like facial sensitivity. This may not be true then, since a higher concentration of sensory holes and nerves are found mostly in semi-aquatic and/or beaked reptiles. Terrestrial non-avian dinosaurs with large nerve networks like Neovenator, Tyrannosaurus, and Erlikosaurus may therefore be hypothesized to have had average facial sensitivity. The authors of the new Tyrannosaurus paper didn't test this particular hypothesis as a larger sample size of living and extinct animals needs to be used. That being said, the inference that dinosaurs with lots of holes in their face bones means that they had a super-sensitive croc snoot was made without reference to preserved nerve data like what is being figured in this paper, so it's not exactly as strongly supported as it could be if the nerve data were included and also supported the croc snout hypothesis. So, what else would the face bone holes and moderately sensitive nature of these face bones mean for Tyrannosaurus, if not a croc snout? The author team suggests a few options. The concentration of nerve canals in the snout and jaw could have led to soft tissue structures like keratinous pads for releasing or keeping heat, or for social signaling, or even for intraspecific displays. There's now a ton of evidence that Tyrannosaurus loved to roughhouse with one another. Healed bites, fractures, scratches, and more litter the skull bones of a ton of tyrannosaurs. A nice patch of hard keratinous dead skin or horny sheaths around this area would help absorb shocks and deflect bites that went a little too hard. This social or sexual display function of the face is consistent with data collected on the neurovascular canals observed in a maxilla bone from a younger Tyrannosaurus. Remember Jane? Jane here doesn't have nearly the complexity in their neural canals that Sue has. If the nerves connected to social soft tissue structures, then the presence of simpler nerves in a sexually immature juvenile and more complex ones in an adult would correlate rather strongly with the presence of some sort of structure whose main purpose is for socio-sexual signaling. Puberty would cause the Tyrannosaurus to grow more nerves to supply the new growing structures. Lips again? Ready for another needlessly complicated discussion on lips? Of course you are, you naughty little… A contentious issue has cropped up over the last few years on how we should reconstruct our beakless theropod dinosaurs. Plenty of older paleoart has them with their teeth sticking out of their mouths all willy-nilly. The thing is that there are very few animals that have toothers that stick out of their mouthers. Those mammals that do usually have tusks, which are made of ivory and are therefore stronger and more resistant than their other teeth. Those mammals that don't have tusks live in the water all the time and use their long teeth for catching fish. Therefore, their teeth are constantly lubricated by water, and having no lips, they can easily release any water that enters their mouths when they go to nab some food. These animals are of course the river dolphins. Birds have no teeth, so they are taken out of the discussion altogether. The only other animals that keep their teeth uncovered are crocodilians. Exposed, non-tusk teeth dry out and fall apart. Biologist Jennifer Creech did her master's thesis on the desiccation of crocodilian teeth. This study found that crocodilian teeth become brittle when out of the water for a long period of time. This proves that crocodilian teeth are kept lubricated by their lifestyle, and that any terrestrial reptile, like lizards and dinosaurs, would need a lip-like covering to lubricate the teeth. However, this is an unpublished master's thesis, and this is only one study. Turns out that a few species of crocodilians will wait out the dry season by hibernating or estivating in burrows for months at a time. They come out of their hibernation with working teeth. This would seem to contradict Creech's study on croc teeth becoming brittle. Obviously, cool, dark burrows are high in humidity, so that could be an explanation for why their teeth don't fall apart during hibernation, but at this point I think we need to move on. The only living relatives of the dinosaurs are birds and crocs. Crocs are heavily adapted to their specific ecological niche of semi-aquatic ambush predator. This means that, like birds, they are a bad comparison when it comes to the facial soft tissues of dinosaurs. We are now left with what can be observed and inferred from the bones alone, and any other similar structures in anything reptilian. Okay, cool. That narrows it down to lizards? Yeah, lizards are pretty distantly related to dinosaurs, but not as much as mammals. Like I said before, most animals have some form of soft tissue covering their teeth. Amphibians, many fish, lizards, snakes, and mammals. This kind of means that a lipped condition is the ancestral trait that appeared as soon as animals adapted to land. You would need a lot of evidence to prove that a group of animals diverged from the lipped condition. Most living lizards have extensive soft tissues in and on their mouths. Gums, lips, and lip scales cover up the teeth. The only thing that is exposed is the very tips of their teeth, but even that is hidden behind their lips. These are not the highly mobile muscular lips of mammals, but they are a lip-like covering all the same. Pretty much every other non-theropod dinosaur and pterosaur has a keratinous beak and intermeshing teeth. A fragment of a sauropod lip was found once, but otherwise, even the sauropods may have had some sort of cornified pad on their mouths. That means only theropods would have had the chance of lips. This may mean that liplessness is the ancestral condition for the Dinosauria, since even their distant cousins, the pterosaurs, are beaked or have teeth too large to be covered by lips. On top of that, most non-avian theropod dinosaurs replace their teeth a lot, like sharks and crocs. Tarbosaurus and Tyrannosaurus are known to have had large holes that would have housed large nerves attached to the salivary glands. That would mean that at least Tyrannosaurs could salivate a lot. If they were constantly replacing their teeth and could salivate all over them like a hungry lapdog, then perhaps they really didn't need lips to keep their teeth lubricated. The likelihood of lips looks more dire when phylogenetic bracketing is considered, at least according to the authors of this new paper. The Dinosauria is deeply nested within the sauropsid group, turtles, crocs, and birds. All of them are toothless and beaked and toothed, or toothed and lipless, except for lizards, but they're super distantly related. They're not even really, they split off really early, so they don't really, they don't really count. This would seem to support a lipless condition as the primitive ancestral condition to the dinosaurs. All living reptiles with lips belong to the Lepidosauria, aka snakes and lizards. Some studies have suggested a link between tooth size and lippiness, while others still have found a correlation between lips and the bone texture of the snout or the way in which the teeth interlock. All have come to opposing conclusions on lips or no lips. Another unpublished master's thesis by Ashley Morhart suggested that a lower number of snout holes organized in a line across the snout would correlate to the presence of lips. You see, crocs have an extremely high number of snout holes and are lipless, while most lizards just have one row of large holes and lips. Most non-avian theropod dinosaurs only have one row of large holes, like lizards, and therefore would likely have some form of lip-like tissue. But, as the authors of this new paper, Boabdallah, Lesner, and Benoit point out, Morhart's study failed to reconstruct a beak in the ornithischian dinosaurs, which are known to have beaks covering their snoots. This may mean her other conclusions don't hold as much water. Therefore, the answer to the question of whether beakless non-avian theropod dinosaurs had lips or not remains unanswered. What do we do now? Even Boabdallah, Lesnar, and Benoit mentioned that it would be tempting to get to work using their Sioux snoot data to hypothesize the presence or lack of lips in these dinosaurs, but it really still is too early to tell for sure. I personally think that the situation is more complex than a full yes or no on lips for all beakless theropods. I think there probably were some theropods with some form of lip-like tissue and some that didn't. Things tend to be muddy like that, but like the authors have cautioned, even my admittedly enthusiasmless nuance is too early to say. More studies like this neurovascular anatomy one need to be done, and more fossils need to be thrown in a CT scanner. With what little is already known and figured, much about the paleobiology of the dinosaurs has been finagled from info on the neurovascular canals. This means that studies of this sort are extremely important for the understanding of the evolution of the soft tissues of the dinosaurs, and ultimately, the birds. For more interesting stories about nature, the history of life, or what goes bump in the night, subscribe, hit the bell icon for updates, like this video, and drop a comment in the comment section below. Thanks for watching. Special thanks goes to my elephant tier patrons Thea Svensson, Staniforth Hopkins, Dinosaur, Chris Frampton, Biotaverse, Arda Bayer, and Christoph Hubbinger, as well as my Tyrannosaur patrons Iron Bladesman, Henry Brennan, Danny Van Heck, and Dana Manchester.